Hi, in the last video we built the DMA design and we got the example software and ran it out of the box straight away. In this video I want to explain a little about the software and maybe do some changes, and I want to show you the XSCT console. This console allows us to actually work all the VTIS features through command line and through scripts. But more importantly, these features allows us to write and read from any memory space obvious by the CPU in control, in this case the ARM Cortex-1. So let's look at our software. First we have the infrastructure. Xilinx has provided us with the DMA, and they also provided us with a software package for this DMA. So we can see here a lot of documentation, releases, and we have two structs. One struct for the xaxidma, which is a struct to work with the DMA, and one DMA config, which holds the part of the DMA itself, whatever we have in it. Also in this software package we have a lot of functions that we will use in our software. Next we need for a DMA transaction two memory buffers, one for the TX and one for the RX, and we need to define them in the DDR. Now the main base address we will use 1 million because the lower addresses in the DDR are for the software itself to run. So 1 million and above we will make the memory spaces for the TX and for the RX. The TX will be at 1 million plus 100,000 memory address, and the TX will be memory base 1 million plus 300,000. A few more parameters. Max package length will be 20. Number of transfers. This software is designed to transfer the DMA 10 times. We don't need 10 times, so we will reduce this to 1. And one more thing we will use is the xDMA struct that we saw here. We defined this for all of the software, for all the functions. After we understood the infrastructure, let's look at the functions themselves. We have three functions. The first function is the main. This is only printf, and it's called the simple poll example function. This is the main function who find the DMA, defined it, work it, and it calls the check data function, which is the last function, which checks the data. As we can see here, the check data function actually looks at the RX, the received buffer, and it generates the data as it was generated in the previous function, in the simple poll example function, and compare. We don't want to compare this to a generated data again and again. We want to compare it to the original data in the TX buffer. So we will add the TX buffer, and instead comparing the loop variable to the value generated in the check data function, we will compare to the TX buffer value. If it's okay, if it's not okay, we will say data error sent and not equal to received fail, and if it's equal, we use the same thing, but we don't return a value. Here we return a value that we failed. We'll write data fine send equal to received path. And of course we don't need the value, we need the TX index. And we don't need the value anymore. Okay. After we fix the file, we need to compile it. Clean. And build. Now we can start look at the main section of the software, which is the simple poll example function. This function is actually doing the DMA configuration, building the data in the TX buffer, and generate the DMA transaction, wait for it to finish, and check the data. For this we can do it in debug mode. So we go here, we go to debug configuration. Again, we see all the, and we move into debug. Since we said the main function doesn't do much except for printing and working the simple example, we go straight to the simple example and make a breakpoint, and we'll run until the breakpoint. Now the first thing we have to do is define our TX and RX buffer. We define them from the parameters above, and we can see here that this was the TX buffer was configured in 0110 and 40 address. So we look at it in the address viewer, in the memory viewer, and the RX buffer was configured to this address, so we will have it too. As you can see, the data here is the data that was generated in the previous run, but we'll ignore this. Now we have the device ID, which was given by the main function, which is actually from the X parameters the definition of the DMA. Here. So this function actually looks for the DMA that is supposed to be in this device ID and configure this struct to have it. If it won't find it, it will not initiate this pointer and the function will fail. And yes, we have a DMA at this device ID, so we passed on. Now we need to take this struct and move it into our struct that we put here to work with. This is just definition for connecting the struct to the DMA in our design. Since we have now a struct for the DMA, we can check if it's scatter gather. This function does that. So we check and it's okay. We disable the interrupts. Those two functions are for that. And this function generates the values in the TX buffer. As you can see, it starts from test start value, which is C. We left it here, and this is why we have C, D, and so on. And every one it increase and work it. So we'll let it run until the breakpoint. But now I want to show you how we can have our odd data at this stage. We can stop the software either by breakpoint or by a wait function, and we can add from the XSCT console, which is a part of the VTIS. If you need to bring it, it's here, if it's not already in your desktop. Now we need a file. For this we need a software for building binary file. I'm using HXD, which is a simple software to read and write binary files. So we put a new file and we write here and we insert bytes. We'll insert 20 bytes with 0, and we have 20 bytes, and now we can write them all. 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, and so on. And we have our file. We'll save it in the software directory. We'll call it in data.bin and we'll save it. Now we'll go to our software folder and we go with our XSCT console to this directory, cd, and the backslashes are on the wrong, should be the other way around. And we're in our directory dir, and we can see the file that we prepared. Now the command to download a file from my PC to the memory in the FPGA design is DOW minus data, the name of the file. I will take it from here, and we have the address. We need to go to get it to the TX buffer, which is in 011000. So 01110000, and since we give him the file, we we don't have to give him the length, because it will run till the file will end. And here we have all the numbers that we wrote from 01, 02 until 20. So we have our new data in the structure. Now we go back to our function and we flash the cache for the TX buffer and for the RX buffer, and the DMA are configured. Now we just need to work them. The first DMA that we start is the RX, the write DMA, because the write will not start until the data will reach him. Now the data will not reach him until the read DMA. So this have to be configured before the read DMA will be configured. So we start and we configure it with the base address of the buffer, with the length of the data that we want to transmit, and which DMA, because we have two in this one. We have write and read. So this is the write. Is this function was successful? Yes. And now we can transfer the read. The read will take the data from the transfer buffer, will take 20 bytes and will send it to the device. The device is the FIFO. Once the FIFO will receive it, it will send it to the write, which is already configured and ready. So the write will start writing it into the memory. And this will take some time, so we have a while loop here. We check the write buffer DMA. The write buffer, if it's busy, it will be the last, because this one works first and then this one will start working. So this will stay busy as long as this one works. So once it's done, you will say, okay, I'm not busy anymore, and it will check if the read is not busy, because the read finished working long ago, and we will move to check the data. So we will run this script all the way, and we didn't see any change here. Why didn't we see any change here? Because the data in the DDR was changed, but we're seeing the cache. The cache was not refreshed, so the cache still shows the previous data. To see the data, we have to flash the cache. This is part of the check data function. So we'll go into the check data function and stop at this point, and we see here cache initialize the buffer before reading it. So we'll run the program until the check, and now we create the buffer for the TX and the RX, and as before we see this is the RX here and the TX here. Next we'll flash the cache, and we got the right data. Now we'll give another breakpoint at the end of this function, and we can run the function. We can run the function, and we see the messages here. Now let's run the function, and now we can see here that the data is fine. We sent 1, we received 1. Data 2 is fine, and so on. So we got the same number, the number we expected. So now I want to show you how we can take again the data from here. If before we took the data from my computer and put it in the FPGA, now I want to show you how we do it the other way around. the command to read from the memory and send it to a file in my computer is mrd minus size in bytes minus bin for a binary file minus file, and we'll give it a name, out data.bin. Now, which address we want to start reading for? 0x01300000, which this is the RX buffer. Next, how many bytes we want to read? 20 hex. And now, if we look at our software directory and run this command from the console, we will see we have a new file, out data file. And if we look at it, we see the same numbers that we got here. So the data was transferred. And that's about it. We configured the DMA. We loaded the data from our computer to our DMA, to the transmit section. We worked the DMA. It read from our transmit buffer into the FIFO. The FIFO immediately generated to the write into the buffer, the second buffer, the RX buffer, and we checked and see that every transaction that we expected got the same number. All the numbers from the TX file, the TX buffer, was received in the RX buffer. And at the end, we read the RX buffer into a file on my computer. I hope you find this video useful. Thank you and goodbye.